Here are some examples for wiring capacitors in series and parallel and how to calculate charge, current, capacitance of the system. First thing we need to do is talk about capacitance. Now remember that capacitance is the ratio of charge to a potential difference across a conductor. So you'll be using this equation right here over and over again, and it's just a matter of which Q and which V do you plug in. Now parallel circuits have two paths that you can go through. So here's your battery, and you can see that if you would trace a path from here coming from the battery, you can either go this way or this way. So these are in parallel. Gives you a path. Now the important thing about parallel circuits is that voltage is the same. All right? You will be using this fact a lot. Whereas in a series circuit, there's only one path. So one path. And in a series circuit, Q is the same. The charge is the same. And you can think about this because if you go from here to here, there's only one path. All the charge that goes in this capacitor has to come through. Here are some of the formulas that you're going to be using. We've already covered this one, where the capacitance is charge over potential difference. In parallel, your capacitance is add. This is because your potential difference is the same in parallel. We derived this in class. In series, it's 1 over the capacitance total in series equals 1 over capacitor 1 plus 1 over capacitor 2 plus however many you have. This is a very important step because remember you have to invert that afterwards. And then you have a variety of energy formulas based on if you have charge and capacitance, charge and voltage, or capacitance and change in voltage. So we're going to be showing you how to use all of these formulas in various set examples. First example, and again I would take a look at this, write down the question, try it yourself, and then start and stop the video as you need to, whenever you get stuck, if you have any questions on how things work. So give you a second to write it down. You can also press pause. Okay. So moving on, you want to find the total capacitance. So what you notice, whenever you start doing these, you have to look at how your circuit breaks down. And if you notice, these two are in, well, what's this? Series. So let's start there. And let's circle here. And if we redraw this circuit because remember, as you keep going, we will redraw this. And let's redraw this as, here's your battery. You have your 3 microfarad, you have your, I'm just going to call this C24. And what is C24? Well, they are in series, so 1 over capacitance in series equals 1 over 4 plus 1 over 2, which equals 3/4. Then remember you have to invert this, so that capacitor in series for 2 and 4 is equal to 4 over thirds times 10 to the minus 6 farads, because it was in microfarads. Alright, so now we have this. We have one further reduction, because now you can notice that these two are in, how are these wired? They are in parallel. So if we look at this, we can say, here's your battery. This is your C parallel, which is the C for the entire circuit. And C parallel equals, in this case, 3 microfarads plus 4 over thirds microfarads, which equals 4 1/3 microfarad. And that is how you get the total capacitance for this circuit, just breaking it down. What we're going to do now is we're going to work on parts B and C. If we examine the circuit, we're trying to find the charge and voltage across this 2 microfarad capacitor. So what we notice is, if I look at this point and this point, because these two capacitors are in series, we know that the charge going across here is a charge going across here, which means that the charge flowing from this side across this equivalent capacitor is the same charge flowing through this whole thing. So let's look at the charge flowing across that equivalent capacitor. So charge, if we rearrange the formula, Again, the formula is C equals Q over delta V. We rearrange this, and we get Q equals C delta V. In this case, the capacitance that we're interested in is the capacitance of this equivalent resistor. Again, because any charge that flows down this branch flows down this branch. And you can determine the charge flowing down this branch because it flows through here. So this would be 4 over 3, not 4 over 3, that doesn't make sense, times 10 to the 6 farads times your voltage, and your voltage is here, which is in parallel with the battery. Voltage and parallel are the same. Good. So this is 6 volts, and you get that the Q on the 2 microfarad capacitor equals 8 times 10 to the minus 6 coulombs. So for the next part, we're going to find the voltage across this. So the delta V across the 2 microfarad capacitor equals charge over capacitance. Now, which charge of capacitance do we use? We'll first take a look. It's the charge flowing from this point to this point, which is the charge going from here to here. Okay, since these are in series, you use the equivalent capacitance. And we know that the charge passing through this equivalent resistor is also the charge going through here. So this is just the one we calculated. 8 times 10 to the minus 6 coulombs over the capacitance. We are interested in the 2 microfarad capacitor, so this becomes 2 times 10 to the minus 6 farads. And your change in voltage, 8 over 2, this would be 4 volts. One last step, and that is calculating the energy across the 4 microfarad capacitor. Energy equals, well, what do we know? This is kind of the hard part. Well, okay, it's all a little confusing, but here's what you've got to look for. You know the total charge from this branch. Again, we figured that out because charge in series is the same. So you said the charge flowing from here to here, same as the charge flowing from this point to this point, across the equivalent capacitance. So we know the charge across the 4 microfarad capacitor. So let's look for something that uses charge, and we know it's capacitance. Is there anything that uses charge and capacitance? Well, right, that is, if you go back to your formula to check, 2c q squared over 2c, which is 8 times 10 to the minus 6 farads squared over 2 times the capacitance, which is 4 times 10 to the minus 6 farads. By the way, top number is coulombs. Sorry, wrote that down wrong. Farads. Which equals 8 times 10 to the minus 6 joules. Key points are just starting here, saying, what do you know? In series, charge is the same. In parallel, voltage is the same. So please work through this. Ask any questions in class. Come to my office. Email. Use the tutors. Lots of resources available. Let's try one more example. Okay. Same example. This time our circuit's a little bit different, but I'm asking the same things. So let's take a look at what we're doing. I give you time to copy this out. Give it a whirl, and then when you're ready, hit play again. To find the total capacitance, again, start out the exact same way. You notice that these two are in parallel. So you know that the C parallel is just the sum of the two together, so this would be 2 plus 4, giving you a total of 6 microfarads. So now we redraw the circuit, and as we redraw the circuit, again, this is an important step. Do not forget to redraw the circuit. It makes things easier. And now these are wired in series. So you know that series, 1 over C in series, equals 1 over, in this case, 3 microfarads, plus 1 over 6 microfarads equals 3 over 6 microfarads. And the important step, remember that this is 1 over CS, so you need to take the reciprocal of this, and you get the capacitance of series, which is the capacitance of this entire circuit, is 2 microfarads. Moving on to the next part. taking a look at this, we want to find the charge and voltage across the 2 microfarad capacitor. Now if you'll look, you see that the 2 microfarad capacitor is in this group here, which is in parallel. What's the same in parallel? Voltages, right. So you know the voltage from this point to this point is the same as the voltage from here to here. So let's solve for that voltage. Again, voltage in parallel is the same. That's why you know from here to here, these are in parallel. Voltage from these points is going to be the same, which is the same as the voltage drop across the equivalent capacitor. So delta V equals Q over C, which equals, this charge. How do I know this charge? Well, if we look at this, this is in series, right? So this charge that flows through this 3 microfarad also flows through the equivalent capacitor. So if we find out how much charge goes through the equivalent capacitor, this gives us a clue to how much charge is going through this whole circuit. So if we look at this, let's say that Q through the equivalent capacitor, again, you know that Q total equals CV. In this case, we're looking at the entire circuit, okay, because we're going to plug this in here. Capacitance total, this is 2 times 10 to the minus 6 farads times volts, 6 volts, equals 12 times 10 to the minus 6 coulombs. Again, the reason we found this is because this is the amount of charge flowing through this circuit, which is the amount of charge flowing through this capacitor and flowing through this equivalent capacitor. So now we know we have 12 times 10 to the minus 6 coulombs, I'm sorry, that is horrible writing, flowing across the equivalent capacitor, which is 6 microfarads, so 6 times 10 to the minus 6 coulombs. Your delta V across that equivalent capacitor, and therefore across each branch of this, because voltage in parallel is the same, is 2 volts. Now that we know the voltage drop across that, we can go and find the Q, the charge on the 2 microfarad capacitor, which we know the voltage, this is C times V. We know the capacitance, again this is 2 times 10 to the minus 6 farads. Voltage, as we calculated above, and you get the Q across the 2 microfarad capacitor is 4 times 10 to the minus 6 coulombs. But we just said the entire charge running through the circuit is 12. So where's the other 8 microcoulombs of charge? Well, 4 went this way, which means 8 goes that way. Final calculation, let's figure out the energy. What do we know? Well, we already know the voltage across this, because voltage in parallel is the same. You know the capacitance, let's look for a formula using voltage and capacitance. I'll give you a second to check it out on your formula sheet. And you can get that this is 1 over half CV squared, which equals 1 over half. Capacitance is 4 times 10 to the minus 6 farads times voltage, 2 volts squared, for a grand total of 8 times 10 to the minus 6 joules of energy stored. I hope this helps, and if you have any questions, just let me know. I'll see you in class.